Building a network means solving a strict physical problem. You have completely different computer systems, and you need them to talk to each other over an unpredictable mix of physical mediums, copper wires, radio waves, or glass fibers. Early network software approached this as a single massive task. Engineers wrote monolithic applications where one block of code handled everything. That code managed the electrical signaling on the wire, checked for data corruption, and rendered the final application interface for the user. This design creates a rigid dependency. If you upgrade your physical hardware, say swapping a slow copper cable for a faster fiber optic link, the electrical properties change. Because the software is monolithic, that single hardware swap forces you to rewrite the entire application stack. By 1984, this was completely unscalable. The computing landscape was densely packed with highly proprietary hardware from different vendors. A terminal from IBM couldn't physically or logically interface with a system from DEC. To grow the network beyond isolated pockets, the software architecture had to be split apart. The International Organization for Standardization proposed a solution, the Open Systems Interconnection, or OSI, reference model. This model introduces the principle of separation of concerns into network engineering. Instead of a monolith, communication is divided into 7 distinct layers. Each layer is entirely isolated. It performs one specific mathematical or logical function and provides that service exclusively to the layer directly above it. This separation is not an automatic improvement. It is a calculated engineering compromise. The cost of layering is processing overhead. Every time data moves between layers, the system has to process and attach new control headers. We trade raw processing efficiency for modularity and hardware interoperability. The OSI model provides an exact taxonomy for how a network should be likely operate. Yet, the strict implementation of these 7 layers contained a specific structural flaw that prevented OSI from becoming the foundation of the modern internet. To understand the architecture, we have to build it from the bottom up. Layer 1 is the physical layer. Inside a computer, data only exists as electrical voltages or light pulses representing ones and zeros. Layer 1 operates entirely without context. It does not recognize frames, it has no routing addresses, and if a pulse is distorted by electromagnetic interference, it has no capacity for error correction. At this physical level, engineers face a permanent constraint, balancing transmission speed against the degradation of the signal over distance, all bounded by the physical cost of the cable. Because physical mediums are noisy and unpredictable, raw bits frequently corrupt. Furthermore, a continuous stream of voltages has no logical start or end point. This gap requires Layer 2, the data link layer. Layer 2 introduces framing. It takes the continuous stream of bits and packages them into bounded blocks, inserting explicit start and stop delimiters so the receiving machine knows exactly where a message begins and ends. To ensure those frames reach the correct destination on a shared local wire, Layer 2 uses MAC addressing. This assigns a physical identity to every node connected to that specific medium. Finally, it addresses the noise of Layer 1. The data link layer appends a cyclic redundancy check, or CRC, to the end of the frame. This checksum allows the receiving node to mathematically verify if any bits flipped during transit. Layers 1 and 2 create a reliable point-to-point transmission system. However, they are strictly localized. The moment data needs to cross a router and enter a completely separate network, Layer 2 logic fails. The limitation lies in the addressing. MAC addresses are entirely flat. If routers used MAC addresses, they would have to memorize the location of every individual device on Earth, creating routing tables too massive to store or search. Layer 3, the network layer, solves this by introducing IP addresses. Unlike MAC addresses, IP addresses are hierarchical. They group devices into structured, branching networks, allowing routers to aggregate millions of addresses into a single directional pathway. But routing data across disparate networks introduces a physical bottleneck. Different physical switches and cables impose different maximum transmission unit limits, meaning they cap the exact size of the payload they can handle. To traverse a link with a smaller capacity, Layer 3 uses fragmentation. It mathematically slices large incoming packets into smaller units that fit the specific physical constraints of the next cable. At this point, IP addressing can successfully deliver a packet to the correct destination machine. But a computer runs dozens of programs simultaneously, and Layer 3 cannot target a specific software process. This requires Layer 4, the transport layer. By assigning port numbers, Layer 4 routes the incoming payload directly to the correct process, matching a web request to a browser or an email to a mail client. Layer 4 also introduces a choice regarding reliability. If an application requires strict accuracy, it uses TCP. TCP enforces flow control and orders the packet sequentially, prioritizing exact stateful delivery at the cost of high latency. If speed is more critical than accuracy, like in live video, Layer 4 uses UDP. UDP strips out the reliability checks, sacrificing guaranteed delivery for immediate low-latency transmission. With Layers 3 and 4 active, the network abstracts the physical cables away. The connection is now entirely logical and driven by the software. In the original OSI model, the top of the stack is split into Layer 5 for session management, Layer 6 for presentation, and Layer 7 for application services. In modern systems, this strict division has collapsed. Dedicated protocols for session checkpointing or translating byte order are largely obsolete. Modern software developers handle those requirements directly within the application's own code. What remains is Layer 7, the application layer. This is the pure protocol interface, like HTTP for web requests or DNS for name resolution, that user applications utilize to request network services. For these 7 layers to work together, they rely on a mechanical process called encapsulation. Even though data physically flows vertically down the stack, encapsulation allows each layer to communicate horizontally with its exact peer on the destination machine. As data moves down the stack, each layer adds a control header. Transport attaches ports, network attaches IP addresses, and data link frames it. At the destination, the process inverts. Ascending layers inspect and strip their headers, passing the pure payload upward. Encapsulation makes true modularity possible, but the trade-off is measurable. Every single header adds physical byte-size overhead that consumes bandwidth on the wire. While the 7-layer OSI model dominates networking textbooks, it did not build the modern internet. That was achieved by a competing, more pragmatic framework, the TCP IP suite. The critical flaw in the OSI implementation was its attempt to engineer a thick network layer. OSI mandated hop-by-hop reliability. In a thick network, every router actively participates in error correction. A packet advances, halts, checks, acknowledges, and forwards. This ensures delivery locally, but globally, overhead compounds. If a packet drops at hop 8, the missing acknowledgement triggers cascading retransmissions backward. This localized retransmission halting forward progress results in congestion collapse. The network layer expends all its processing power trying to manage its own reliability, stalling the actual throughput of data. OSI's thick network architecture was perfectly suited for a highly predictable telephone system where circuits are reserved in advance. It was mathematically incapable of surviving a chaotic, interconnected global web. TCP/IP succeeded because it adopted a radically different engineering philosophy known as the end-to-end principle. Rather than building a thick, intelligent network, TCP/IP stripped all reliability functions out of the IP layer. It created a dumb network where routers act exclusively as stateless, ultra-fast forwarding engines. It utilized connectionless datagrams. Packets traverse the infrastructure completely independently of one another. There are no pre-established virtual circuits, and no router reserves memory or resources for a specific transmission. To handle errors, TCP/IP relied on smart endpoints. All the logic for error recovery, sequencing, and flow control was pushed entirely to the outer edges, managed strictly by the TCP layer on the originating and receiving machines. If a congested router blindly drops a packet, intermediate routers do nothing. The flow continues until the receiving computer detects a sequence gap and requests a specific retransmission directly. Under extreme load, a dumb network won't collapse under cascading hop-by-hop errors. It achieves graceful degradation, prioritizing continuous movement over localized perfection. In the final accounting, the OSI model succeeded in providing the vital taxonomy we use to understand network logic, but TCP/IP provided the functional blueprint that actually worked. TCP/IP won because it accepted that physical networks will always be imperfect. By stripping complexity out of the core infrastructure and pushing it to the endpoints, engineers built a system capable of infinite scale.